Alrighty, 11:15. Let's dive back in. So, uh, MO theory is difficult, and it's definitely something that is important that you know about. Depending on where you go from here with this chemistry, it may become all that you do, or you may never think about it again. And chemistry, this level of chemistry, I don't know which one is true for you, so it's helpful to have seen it at least once. Yet again, as if you ever go into any aspect of trying to predict with high accuracy very complicated molecules. So, for example, if you were a biologist trying to predict the structure of a protein, it's helpful to understand MO theory, as that's ultimately the rules that dictate how a protein folds. If you were to become a electrical engineer or material scientist work something with very complicated molecules and crystals, the basis of how we discuss and predict those properties all lie in this molecular orbital theory. There really aren't many substitutes for it. However, without knowing exactly sort of where you're headed here with your chemistry, we're going to attempt to sort of take the results of MO theory for a relatively specific subset of our periodic table. Again, largely our discussion within this level of chemistry is talking about sort of the first two or three periods, the smaller atoms, the smaller elements found within the periodic table, which occur most readily. And one thing that we see, particularly, for example, the case with sodium and chlorine forming this ionic bond, is that the end result is that sodium has effectively transferred its single 3s electron over to the shared orbitals, which are essentially just the same as chlorine's 3s and 3p orbitals. At the end of it, if you were to rewrite their electronic structure, you would see that sodium, by losing its extra 3s electron, now has its highest valence electron, that is 2 in the 2s and 6 in the 2p, which is the exact same electron configuration as the preceding noble gas neon. One reason why we write the electron configuration in this noble gas notation is that every time we either complete or remove to a completely filled shell, so we remove all three level electrons, we end up exactly at the same configuration as one of our noble gases, in this case, neon for sodium. Chlorine, having effectively gained one electron, now has a completely full 3s and 3p shell and subshell, and now has the same electron configuration as argon, one element to the right. These we would call being isoelectronic, same electronic structure as one of the noble gases. And one of the big results from the from MO theory is that most elements, particularly these smaller, lighter ones, will try to want to achieve a electron configuration, again, isoelectronic to a noble gas, which in many cases requires having 8 valence electrons. Quite often, 2 in an s orbital and 3 in a p orbital. Sort of one of the things that we've noticed, there is some rule that people come up with in the past to try to explain why the magic number of 8, but really it falls out from this MO theory analysis. We see that this set of 8, which we sort of term the octet rule, is a generally hard and fast rule that applies for maybe 80% of the periodic table. That most elements, through a means of either sharing electrons through a covalent bond or transferring electrons through an ionic bond, either gaining or losing, are trying to complete a full shell, a full set of 8, a full set of the 2 or shell, full set of the 3 shell. The one exception being things like hydrogen, or things found in the first level. The first shell, the 1 shell, only has an s orbital, so things like hydrogen and helium, as well as the lighter elements, are happy with just 2 electrons in the 1 shell, since that's a complete version for the 1 level. But nonetheless, this octet rule is a handy way for us to try to figure out how many valence electrons does an element start with, how many does it need to gain or lose to get this nice full complete set of 8. In some instances, they may do so by transferring to form a cation and an anion, like in sodium and chlorine. Any element, things like including things like oxygen, can also achieve this octet rather than by transferring if it doesn't have enough pulling power, enough electronegativity to completely steal an electron, can achieve this octet by sharing. we see that between these two oxygen atoms, each oxygen starts with 6 valence electrons, 2 in the 2s, 4 in the 2p. And effectively, this double bond, the two net bonding orbitals, is a way for these two oxygen atoms to share a set of 2 electrons between them. They each can consider that they have 8, even though 2 of them are sort of joint custody split between the two. So most of our elements, particularly again those found in these upper levels, we can get the same result as MO theory if we apply this octet rule in this particular set of logic. We would be able to predict whether it's ionic or covalent, whether it's transferred or sharing electrons based off this difference in electronegativity. But this gives us a way to begin to assemble more complicated structures than just 2 atoms bonding together, increasingly more and more complex molecules from there. The way that we might represent this graphically and begin to solve these ultimately 3-dimensional structures is what we would call a Lewis structure. This octet rule, again, mostly true for smaller elements, we can sort of show in a much more graphical way for something like oxygen. In these Lewis structures, we draw the elemental symbol, and we draw up to 8 dots surrounding this elemental symbol to represent the 8 electrons this element is trying to achieve. Both these oxygen atoms, before they form their bond, each start with 6, so not yet a full complete set of 8. Because there's only 12 to go around, they can't transfer each other. They'll only ever have 6 if they completely treat their electrons as their own. And so the only solution that these oxygens can carry out to have a set of 8 to call their own is to share these 2 electrons between each other so that this oxygen will count that it has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it considers its own. And this oxygen similarly will have 1, 2, 3, 4, 5, 6, 7, 8. And each this way, by sharing this 2 pairs of electrons, they each consider that they've satisfied their octet rule. A couple things to notice as a result of this Lewis structure analysis. We once again sort of see the formation of 2 bonding pairs of electrons that we saw from the 2 bonding orbitals from MO theory. So we do see sort of the idea that there's a double pair of shared electrons that pulls these 2 oxygen atoms together. But a consequence of this Lewis structure, one that sort of does exist in the real world, is not necessarily always a true interpretation, is that in addition to the shared electrons, each oxygen does retain some of its own electrons that are not shared, that are completely to one atom versus the other, that are not involved in bonding between these 2 oxygen atoms. Any pair of electrons within this octet, within this set of 8 that isn't shared or transferred, isn't part of a bond, we typically refer to as a lone pair. These lone pairs, even though they're not part of bonding, are still negatively charged particles, are still a source of electrostatic repulsion that will ultimately help to dictate the shape of some of these molecules in this particular interpretation. So quite easily, we can use these Lewis structures to predict a lot of bonding information for relatively simple things. We'd also be able to use this idea to show that nitrogen, N2, the form of nitrogen gas that makes up 80-something% of our air, is really coming from the fact that each nitrogen is going to have 5 electrons that can call its own. In order to have a set of 8, each nitrogen is going to need to effectively share 3 electrons between those 2, such that this nitrogen considers that it has 1, 2, 3, 4, 5, 6, 7, 8 set of electrons. Same for the other nitrogen. This nitrogen, in addition to being bonded through a triple bond between these 2 nitrogen atoms, this nitrogen will have 1 lone pair compared to oxygen's 2 lone pairs. We can also see for chlorine, again, on our far right of our periodic table, chlorine has 7 valence electrons. It is 1 short of a full set of 8. And if it can't find something like a sodium to completely give up an electron to it, let's say chlorine needs to bond with chlorine to make chlorine gas, the thing that disinfects your swimming pool. This chlorine with a identical chlorine, it's going to have to share a pair of electrons between the two. Still, once again, we can count 1, 2, 3, 4, 5, 6, 7, 8 electrons for that particular chlorine, satisfying this octet rule. Each chlorine is going to have one bond, a single pair of shared electrons, as well as 3 sets of lone pairs. We can see sort of by this set of analogies that every atom under this octet rule, as we draw these Lewis structures, is going to want to have 4 pairs of electrons around it. It may be divided up between 3 bonds and 1 lone pair, 2 bonds, 2 lone pairs, 1 bond, 3 lone pairs. Or in the case of something like our noble gases, which start out with a full set of 8, we can see that neon, with full set of valence electrons 8, already satisfies this octet rule, which leads to our prediction and the observation that neon, like every noble gas, doesn't need to bond with anything to satisfy its octet rule. Neon, helium, argon are having to exist as singular atoms, no bonds needed, no shared or transferred electrons, because it's already satisfied its octet rule through 4 lone pairs. This Lewis structure analysis, again, there's lots of exceptions, and a lot of chemistry textbooks spend some time modifying these rules to help you better predict things. Different applications of chemistry require different levels of detail for that. But for our purposes, we can take this as sort of a trend to begin to describe how each different column of the periodic table tends to bond and tends to form these shared or transfer set of 8 octet electrons. We see that whether it's nitrogen, oxygen, chlorine, or one of our noble gases, we see a different pattern begin to emerge of how to satisfy this set of 8 electrons. It allows us to now map out our periodic table, map out each of these groups in terms of what we would predict in terms of transferred or shared electrons, how many electrons are likely to be transferred to form cations and anions, versus how many shared bonds might be formed for a particular species. If we look at ionic compounds, things that have large differences in electronegativity, so they're more likely to just give up their electron and completely steal an electron, everything found in this first column, including things like sodium and potassium, all have this one extra spare awkward s electron. Because these are relatively low in electronegativity, easily give up these electrons, all of our alkaline metals found here in our first group, our first column of the periodic table, will all tend to want to just give up that 1 electron to satisfy its octet rule, referring to the shell lower. And so all of our alkaline metals are described by typically forming a +1 cation by losing that 1 electron. So we're most likely to see sodium as sodium plus, potassium plus, rubidium plus, so on and so forth. It is very unlikely that we would see something like sodium 2 plus, having lost 2 electrons, because now it would violate the octet rule and would only have 7 of the 8 desired electrons. Our periodic table, again, laid out as a map, would suggest that 1 column over with 1 more valence electrons, something like magnesium with 2 3s electrons, will tend to want to lose those 2 electrons to again revert and be isoelectronic to the preceding noble gas. So all of our alkaline earths, magnesium, calcium, strontium, so on and forth, barium, are all going to tend to want to form +2 cations by completely giving up that electron to satisfy this octet rule. The thing that it might give it up to might vary. And we see particular variability again with this D block found in the middle, also our F block as well, which we don't talk about quite as much. These D blocks, again, because we have not yet talked about these D orbitals, complicates our very simple octet rule. But the main takeaway should be that these will tend to want to also give up a variable number of electrons, typically forming cations by losing electrons rather than gaining electrons. We have much more predictive capabilities when we talk about the right side of our periodic table. Again, things like chlorine only have 7 of their 8 valence electrons, so they tend to want to gain 1 electron by stealing it from something like sodium. And so our seventh group, the 17th column of our periodic table, the halogens or halides, will tend to want to gain 1 electron like chlorine, forming Cl-, or fluorine minus fluoride, bromine minus bromide, so on and so forth. Oxygen, as it engages in ionic bonds, not always, but as it engages in ionic bonds, is able to steal 2 electrons to gain the 2 it's missing, completing its set of 8. So oxygen, sulfur, other chalcogens or chalcogenides will tend to want to form a 2- anion. Potentially, you may have observed that in our lab last week, we formed magnesium oxide by magnesium transferring 2 of its electrons to form magnesium 2 plus, and giving those 2 electrons to oxygen to form oxygen 2 minus and to form the compound MgO. Each of them satisfying their octet rule by transferring the electrons between these atoms of quite different electronegativities. Other sort of general trends we can also map out for these covalent bonds, these shared electron cases. Just as we have seen before, hydrogen, by being in this first column, really has a spare extra 1s electron. Hydrogen, to complete its one shell, will either want to gain 1 electron or lose 1 electron to completely fill it out. Depending on the instance and example, sometimes it will lose 1 electron to be a +1 cation, like sodium, like potassium. But as it must share electrons with certain elements with similar electronegativities, hydrogen will want to gain 1 electron or 1 shared electron, so typically form just a single bond. Very rare, nearly impossible to form more than 1. Halogens and halides, like chlorine, if it has to share an electron rather than completely getting custody of 1, it's going to share 1 by forming a single bond, such as we saw between chlorine and chlorine. Similarly, oxygen, for similar reasons as we said before, will tend to want to form 2 total bonds. Might be 2 bonds to the same oxygen, might be 2 bonds to different atoms, but a net total of 2 bonds to get its full set of 8 shared electrons. Our nitrogen group, also called the pnictogens or pnictides, will want to have a set of 3 bonds, as we saw with N2 gas, a triple bond between those 2 nitrogens. And carbon will tend to want to form 4 bonds in total. Again, carbon starts with 4 valence electrons, 2 in the 2s, 2 in the 2p, and will want to gain 4 electrons somehow, quite often by sharing through a covalent bond of some description. Beyond these far extremes of the periodic table, our ability to predict things become a little more tricky. You might think that boron should be able to be interpolated or predicted between how the preceding beryllium behaves and following carbon behaves. But again, there are gaps in our octet rule, in our Lewis structure analysis, that aren't able to predict how things like boron will behave. Even something like silicon, found 1 right below carbon, tends to want to form 4 bonds, but as it gets larger, silicon begins to do things that begin to break a lot of the rules of our nice convenient octet rule. So we use this octet rule to really talk about a very limited but most common set of chemicals and compounds we encounter. But just be very aware that there are limits to this theory, and there are places in which these estimations of trying to satisfy this octet do fall apart. Some of those exceptions are very exotic. They deal with things like uranium and thorium that behave completely different to all the rules we've talked about thus far for the octet rule. But there are some just very notable to be aware of places we see certain elements break the octet rule. Now, it doesn't break MO theory, and one reason why we introduce molecular orbital theory is that molecular orbital theory, looking at the combinations of orbitals, is able to account for why some atoms, some elements, are happy with only a set of 6 valence electrons, and some others require more than 8, 10, or 12 valence electrons. As far as this octet rule is concerned, these are just noted as exceptions, places where it breaks down. Some elements, things like beryllium, found just in the second column, second period, BE, beryllium is quite happy with significantly less than 8 valence electrons. It is happy with just 4 valence electrons for reasons, again, predicted by MO theory, but not predicted by this octet rule. Boron, 1 over from beryllium, is happy with just 6 valence electrons, here shown by 3 single bonds. And so there are instances in which less than 8 is okay as far as these molecules are concerned. There are also many instances in which we have hypervalent molecules that have way more than 8 electrons. Something like sulfur hexafluoride, which is a denser than air gas used in electronics manufacturing. If you've ever seen those science videos, which are actually quite dangerous, of people breathing in helium, which is a less dense than air gas that makes people's voice higher, sulfur hexafluoride, this combination of sulfur bonded to 6-fluorine, is significantly denser, is significantly more dense than air, and makes people's voice extremely unusually low. It is an asphyxiant, so if you breathe in too much, you will kill yourself, and which is why we don't typically do it as demos, because it's actually a very bad thing to do too much of. But you'll notice that this sulfur found in the middle is bonded to 6 different fluorines. Each of these 6 single bonds accounts for 2 valence electrons. So this sulfur is very happy to have 12 valence electrons, more than the 8 we would predict with this octet rule. Same thing for this iodine, so on and so forth. We even see weird exceptions like xenon, found here. Xenon, we would normally predict, and does exist as a pure atomic element, being a noble gas. Xenon has a full set of 8 valence electrons. We would predict xenon would not react the same way that helium and neon do not react. But for reasons that violate our octet rule, predicted by MO theory, xenon now bonds to 4-fluorine for a total of, once again, 12 valence electrons. So a lot of this, again, is things that we don't deal with too much at this level of chemistry, but it's important for you to understand that there are limits to this simplified version of bonding rules as we showed. For this course, we'll typically be able to get away with a lot of these octet rule and approximations, informed a little bit by MO theory, just to sort of anchor some of the reason why these rules exist. As you move through your studies, you may encounter and have to deal more readily with these exceptions to our simplified rules. So most of our discussion till now has really treated these things as just atoms bonded to other atoms to know what's connected to what. But we haven't really said too much about how these things are arranged in a 3-dimensional nature. Again, one of the big results from MO theory was to predict why water, H2O, is a bent molecule as opposed to a linear arrangement of HOH. And similarly, this octet rule has to somehow account for being able to predict the shape of these molecules. Why this HBeH is a linear chain of these 3 atoms versus H2O was a bent sort of angle chain of those 3 atoms. So we need to add things to this octet rule to help be able to predict not just what's bonded to what, but what these molecules look like in 3 dimensions to better predict their behavior. We're going to take a look at the molecule of methane, CH4, and feel free to follow along, but we'll go through an example of how we might use a Lewis structure to begin to, 1, figure out how this is bonded, as well as to figure out a 3-dimensional structure. So we'll draw our Lewis structure first by elemental C for carbon, and we'll look at our periodic table. We'll either reference the idea that carbon has 2 s valence electrons and 2 p valence electrons, or by being in this carbon group, this 4th group, we would predict that carbon should have 4 valence electrons. And for the moment, because electrons are all negatively charged, they like to repel each other, I'll draw them on 4 sides of this sort of carbon elemental symbol. These have to combine with hydrogen. I have 4 hydrogens, and each hydrogen is going to be the same. It's going to have 1 valence electron, this being the 1s electron. Now, some of this is sort of puzzle making. Some of this is a little bit of guess and check. And we'll go through several examples of these to get some practice with it. But you may sort of already intuit and see that there are 4 electrons that this carbon needs to gain, either through sharing or transferring, and each hydrogen has 1 that would like to either give up or gain 1 more by sharing. So a reasonable prediction for our Lewis structure for methane, CH4, would put our carbon here in the center with its four evenly spaced hydrogens, four evenly spaced valence electrons. And around that, we'll surround it with our hydrogens such that each of them can share an electron with this carbon. In this way, by arranging it as such, these single electrons can act as a shared pair between those two. And we would begin to assemble a Lewis structure that shows that this carbon is bonded to 4 hydrogen. This carbon now has 2, 4, 6, 8 valence electrons to satisfy its octet, and each of these hydrogens has 1, 2 electrons to fill out its 1s shell, its version of the octet rule. And if you're to look up online, and again, this is an open resource class, and I don't spend too much time going over Lewis structures because the results are pretty much all known to the rest of the world. And in many cases, a lot of guesswork can be eliminated by looking up a structure for simple as well as complicated molecules. If you were to look up the Lewis structure or a representation of the structure of methane, this is what you would find on Google. Very much the result we derive from satisfying this octet rule. However, if you were to actually look at a molecule of methane under a very, very intense microscope, maybe an electron microscope that can image single atoms, single molecules through very unique optics, you wouldn't see this sort of cross flat structure of carbon with hydrogen at each of the cardinal directions, north, south, east, and west. You will see this little lumpy thing floating around into your microscope that sort of shows a different arrangement of these 4 things, now distributed in a different pattern, not a cross, not a flat molecule, but sort of this lumpy pyramidal shape. So the challenge and the question and the limitation of Lewis structures on their own is that it doesn't really predict the structure in 3 dimensions. Every Lewis structure that you will draw is going to be a flat 2-dimensional object, but very few molecules are going to be flat 2-dimensional molecules. They'll have some 3-dimensional structure. And how we predict that really just goes back again to this idea that electrons are negatively charged particles that repel each other. Negative signs repel negative signs. And we can build some physical intuition. And you may have done this in high school before or other classes to sort of figure out how do different numbers of things arrange themselves in 3 dimensions. So quite sensibly, if I were to, for example, have 2 sets of things coming out of a central atom, let's say I just had 2 single bonds, the easiest way to arrange 2 things around a central atom is in a straight line. This straight line has the most space between my 2 sets of bonds, my 2 sets of repelling negatively charged electrons. So if I just have 2 things surrounding a central atom, in many cases I would predict a linear arrangement with a 180-degree bond angle between those 2. If I add a third thing, and let's say I have 3 things surrounding my central atom, the best way to arrange 3 things is in this trigonal pyramidal shape with 120 degrees between each of those things. So we can build a lot of physical intuition by how physical objects repel each other, just as the way electrons might repel each other. We can also begin to see some variations on the theme. As I've shown it, these 3 things surrounding this central atom are all equal in size, more or less. So this might represent the 3 different single bonds coming out from boron, which is happy with 6, that arrange themselves in this trigonal planar shape, all lying on the same plane. That is different, though, than if I was to have 2 bonds and 1 lone pair. A lone pair, just like a bond, is a set of electrons that repels each other, but a lone pair is just a set of electrons, versus a bond is sort of balanced out by the positive charges. So typically when we look at lone pairs, such as the ones found surrounding my oxygen atoms, as we look at these lone pairs now still repel each other, just as this bond between oxygen does. But lone pairs, by being unbalanced by any positive charges, are going to be typically larger in repelling sphere than the other ones. And so, trying to decide whether to make this balloon smaller or larger. Well, we'll try. If you're not a person that likes balloons and doesn't like balloons popping, I'm sorry, this is not the unit for you. As we are looking at how these are arranged in 3 dimensions, the fact that a lone pair is slightly larger, more repulsive than a bond does, has some consequences for the shape and the angles we see. We would see that now if we arranged 2 bonds in a lone pair, we begin to see that they repel each other a little differently. This lone pair is now much more repulsive than these smaller pairs of bonds. And we'll see that this angle gets pushed down. So rather than being 120 degrees, this begins to shrink towards 115 degrees, 110 degrees, so on and so forth, depending on the exact arrangement of those things. As we begin to assemble these shapes, most of our arrangement of atoms, whether there are 2 things, 3 things, 4 things surrounding our central atom, all adopt sort of a similar parent structure, modified by how repulsive one particular set of these things are. So, quite sensibly, we would predict for 2 things surrounding a central atom that we would have a linear shape. As we move to 3 things, we have generally a sort of trigonal planar shape. But the question for methane is, what shape do we get when we have 4 things surrounding our central atom? I request some balloon blowing help. Someone like to blow a balloon. I'm unhappy shaking of heads. So if I blow 4 bonds and have them all roughly the same size and shape, my 4 equally spaced size shaped bonds should now all repel each other equally as each other. But what shape does that make, and how do we begin to interpret that? As a hint at sort of what we saw leading up to this, as we sort of add a 4th thing to the mix, we begin to form not a sort of 4-sided pyramid, but this sort of 3-sided pyramid shape. We begin to form a thing that tries to distribute all 4 things as evenly as possible, as much as we can, and we begin to form variations of this arrangement of 4 things. You would find that sort of on a geometric basis, this is called a tetrahedra from the 4 things evenly spaced throughout this system, with a very matching angle of 109.5 degrees between them, which really just comes out from the geometry of this 4-sided Platonic solid. So as we begin to form these structures, our job here is to try to maximize the distance between these repelling pair of electrons that might come from lone pairs, that might come from bonds, all of them trying to maximize the distance from each other. We complement our analysis of 3D structures, of Lewis structures, these flat 2-dimensional shapes that just shows what bonded to what, by what we call valence shell electron pair repulsion. The idea that each bond, each electron lone pair is going to try to repel each other as much as they can. If you want some balloons to take with you and sort of play with balloons on your own, I'm happy to leave you with some. But the result of this is that we sort of have a roadmap that shows us, based off of how many things are surrounding our central atom E, and how many lone pairs versus how many bonding things, we can adopt different types of geometries. There are certainly very exotic molecules, ones that are hypervalent with 5 or 6 things attached to them. But in this course, we'll spend most of the time dealing with things that have 2, 3, or 4 bonding partners. Our shapes, again, are derived from trying to evenly space things out as much as possible. For a linear thing with 2 things surrounding, we try to space them out as much as possible, so 180 degrees from each other. With 3 things, we adopt this trigonoplanar shape, this 120 degrees between each of our bonding pairs and partners. As we begin to substitute larger and larger things, we begin to push down on this bond angle, shortening it or narrowing it from 120 to something less than 120. Hard to say exactly without knowing more information. And similarly for our tetrahedral shape with 4 things surrounding it, in the case of methane, we can predict that since we have 4 equivalent bonds repelling each other, we form this nice classic tetrahedral shape with exactly 109.5 degrees between each of these bonds. As we begin to switch out some of these bonds for lone pairs, again, the lone pair begins to repel and push down even larger. So as our lone pair is larger, more repulsive than the others, we begin to sort of push down on this structure, shrinking these bond angles, deviating from this perfect 109.5 degrees. The amount that it distorts is very much dependent on how big these electron clouds are, what the orbital energies are. So we can say more qualitatively, relatively, that we have something less than 109 degrees between those. And certainly as we go towards a structure that has two bonds and 2 lone pairs, we start to squish those bonds down even more, much less than 109.5 degrees. So a lot of this is very much something that you can look at pictures and look at things, but it's helpful to get your hands on stuff and to be able to touch and feel. There's sort of a weird gap in chemistry in that a lot of what we do is 3-dimensional in nature, is something that calls for a very tactile, kinesthetic approach. But as it is, everyone here has to sit through a lecture which presents images on a flat 2-dimensional screen. You have to take tests that exist on flat 2-dimensional paper, and so we're always limited in how we're able to represent complex 3-dimensional shapes in the medium in which we normally teach. So a lot of chemistry that you'll see represented, including in this class, is going to require us to make representations of 3-dimensional shapes now in a 2-dimensional or maybe 2.5-dimensional drawing or some sort of flat representation. So let's look back at our molecule of methane. In addition to balloons, chemists, particularly if you were an organic chemist, really have to worry about the 3-dimensional shapes of things. We make abundant use of molecular models, which are very handy physical teaching tools. I figure out how to divvy things up. I think you can share it. 2 amongst 3 of you. So each of these molecular model kits a portion of it, certainly. You'll notice there's a bunch of different parts. There are a bunch of spheres, which represent atoms, as well as a bunch of straight connector pieces, which represent bonds. Each straight connector piece represents a single bond. And the wonderful thing about the molecular model kits is they build in a physical intuition. You can touch and feel these molecules, and you can actually feel how they're arranged and the forces present within each. So we're going to build some molecules for ourselves to actually get our hands on them. So dump out your little kit for yourself. Within this model kit, the different colors importantly represent different atoms, different elements. Typically in these kits, you'll see that the tiny white balls represent a hydrogen atom. Quite intuitively, you'll see that this hydrogen atom has one hole for it to represent that hydrogen really likes to form one bond, one covalent bond. So there's only one hole going to this hydrogen. You'll see that the black sphere usually represents carbon. And again, quite intuitively, this black sphere has 4 holes attached to it to represent that carbon usually likes to form 4 covalent bonds. The red one usually is representing oxygen, and your blue or purple, with different kits have different things, features a nitrogen atom. So take a moment with you and your buddy to make me a molecule of methane using this kit.
Sorry, what's the white versus purple bonds?
No difference there. You'll notice that there are some shorter and longer bonds. you'll probably want to use these shorter bonds for these single bonds between carbon and hydrogen. So make your molecule of methane, and then we'll all hold up our result. And if you're wrong, then you'll quickly hide it and correct it. But the lucky thing about these molecular model kits is that it's very hard to get a wrong structure because these only connect in the rules in which atoms connect. They're sort of a shortcut to predicting structures because these cannot break the rules of chemistry. If you can make a thing, it must exist. So if we're all ready and happy, we're going to hold our model. We should all have the same model, the exact same model. We're going to hold it up in 3, 2, 1. Hold it up. Wonderful. Everybody seems to have the same thing. And so take a moment to look at this model. This is a classic, again, tetrahedral shape. And no matter how you rotate it, you'll see that every hydrogen-carbon-hydrogen bond has the exact same angle. Depending on how you hold it, you may sort of see it looks like a pyramid or as sort of this sort of offset rhomboid structure. But this tetrahedral structure should have each carbon-hydrogen bond equally spaced out from all the other carbon-hydrogen bonds as possible. If you were to measure this with a protractor, you'd find this is exactly 109.5 degrees. Now the question is, it'd be wonderful if every test you had and you took, you had a little molecular kit, and if someone asked you to draw a molecule, you could just show them your little structure and you'd be done. You have a perfect three-dimensional representation. Unfortunately, that's not how the real world exists, at least at this level of technology. And so the question is, how do you draw this on two-dimensional paper without reverting to something that really doesn't represent what the structure looks like, which would look like this sort of Lewis structure as is? So as you rotate it, you'll probably notice you can probably hold in one orientation in which at least two of the bonds lie in the same plane of the page. So this 109.5 degree angle, you could fit that in one plane of the page. So you could draw that as a flat two-dimensional structure. But you'll notice that in that orientation, you'll have one carbon-hydrogen bond pointing away from you, one pointing towards you, which again represents this three-dimensional nature. How do chemists draw that? Well, within the standardized nomenclature of us as chemists, the way that we represent three-dimensional structures is with a wedged bond notation. If you see a structure like this, as you look at structures, you will notice that we represent any bond that lies flat on the plane of the page, such as the hydrogen-carbon, carbon-hydrogen bond. We'll use single normal straight lines to represent that. To represent that the one carbon-hydrogen bond is pointing away from us into the plane of the page, we'll have a dashed bond that wedges out sort of in the direction pointing away from us between this carbon and this hydrogen, and another solid wedge bond pointing towards us, representing the last, fourth, and final hydrogen present here. So this structure is interpretable by every chemist out there to represent not just the fact that there's 4 hydrogens bonded to this carbon to satisfy the Lewis structure, to satisfy the octet rule, but it lets us know the shape in 3 dimensions. Sometimes you'll see people are a little lazy or don't like to draw pictures, and they will represent this non-three-dimensional Lewis structure. And it is to your benefit to be able to interpret and translate from this flat, unrepresentative 2D structure into either a sort of 2.5 dimension version or ultimately a 3-dimensional version of that molecule. For our purposes, I insist that you draw them using this dashed and solid wedge bond notation, just so that we can all have the same 3-dimensional molecule in our minds. Let's do a couple more of these just to get some handle and practice on it. Let's make a molecule of ammonia. So ammonia, being NH3, will work together to draw the Lewis structure. So ammonia, NH3, we would predict is consistent of a nitrogen with 5 valence electrons, found 1 over to the right to carbon, so have 1 more valence electron than carbon does. And this needs to combine with 3 of those hydrogens, again, each with a single valence electron. Potentially inspired by what we saw with methane, again, analogous molecules, we can make some analogy to it. we will potentially draw our Lewis structure of nitrogen, like methane, surrounded by those 3 hydrogens, such that the shared electrons can help satisfy nitrogen's desire for 8 and hydrogen's desire for 2. So according to the structure, we have something very similar to what we saw for methane. Of carbon surrounded by 4 bonds. Now nitrogen, in a similar variation, has 3 bonds and 1 set of lone pairs. Now, depending on the exact nitrogen atom that I gave you, if you would like to represent the lone pair on a nitrogen, that's what this little lobe structure represents. Again, 2 little dots representing the set of electrons. But you'll probably notice that your nitrogen atom either has 3 or 4 holes, to either represent that there are 4 total things surrounding for this valence electron set of 8, or the fact that nitrogen usually forms 3 bonds and 1 lone pair. So depending on which actual one you get, you're welcome to substitute in the version that makes sense for you. So everybody take a moment to make me a 3-dimensional molecule of ammonia.
How would we make this lone pair have more propulsion if they're all equal space?
There are some limits to this kit, and we'll see what that looks like in a moment. That's a good point. All right, does everyone have their ammonia molecule with either 3 or 4 things surrounding it? Again, these molecules are nice because you cannot create incorrect Lewis structures out of them. Nitrogen with 3 holes or 4 holes can only bond to 3 or 4 things depending on the exact structure. You'll never be able to attach 6 things to a nitrogen, so you'll never be able to sort of incorrectly count this octet set of 8. All right, we'll hold up our ammonia molecule in 3, 2, 1. So we should all have something that looks quite similar, quite reminiscent of the methane molecule we had. That if you sort of hold it, you'll see that the 3 NH bonds forms the 3 sort of lower halves of the tetrahedral shape that we saw before. And effectively, we substitute one CH bond for this lone pair on the nitrogen to reflect that nitrogen has 1 more electron, doesn't need to form that extra bond. Of course, this being similar in a tetrahedral shape, these bonds are technically pushed a little narrower, ever so slightly, a few fractions of a degree, by this larger, more repulsive lone pair up top. But we see again sort of this repeating pattern that similar arrangements of repulsive electrons form similar analogous shapes. What we would see, however, in nature would be, we can't really visualize lone pairs in the same way we view atoms, but we would see sort of the same structure, but now represented by what we would call a trigonal pyramidal shape. Still sort of like the tetrahedral, but now only featuring sort of 4 total atoms, 3 bonded to 1. We will represent this in 3 dimensions, and you should spend a moment to orient it so you can understand and visualize where these dashed and solid wedge bonds come, where they look, where they appear. Some structures will show the lone pair, some others will not. So it depends on what you're trying to highlight. But we'll notice again that we always adopt a 3-dimensional structure, one that features bonds coming into the page, ones that come going out. It's quite important that our Lewis structure with a 4th set of electrons as the lone pair tells us that we have this sort of trigonal pyramidal shape as opposed to what we would expect for just 3 bonds of a trigonal planar. The fact that this one is slightly bent, slightly puckered, as opposed to a purely flat trigonal planar shape will have a lot of effect on the properties of this molecule that we'll come to in the coming weeks. All right, let's do a few more. So we already talked a little bit about water, but we still build the intuition of these molecular kits. If you'll build me a molecule of water, we'll inspect it together just as before. So you'll find that this molecule of water, unlike our Lewis diagram might show, does not give places for these lone pairs. Different molecular model kits will have different specifications, all sort of hinting to the same idea that water here, with an oxygen with 6 valence electrons, our Lewis structure would, not incorrectly, but quite simply, or sort of too simply, show the idea that in order for oxygen to satisfy its octet, it needs to form 2 shared sets of electrons, so 2 pairs of bonds. But rather than it just being 2 things arranged around the central oxygen, our Lewis structure shows us that there's also 2 sets of lone pairs to give, again, a total of 4 things surrounding this oxygen. So we would predict once again that the way to arrange 4 things, bonds and lone pairs both included, would be as this general tetrahedral shape. But as everybody should hold up their water molecule, you'll notice that the overall general shape will be one that really just looks like a bent structure. Whether we are able to model it or must envision it, we can recognize that this is effectively just 2 of the 4 legs of our tetrahedral shape, with our lone pairs sort of either conceptually or quite there visually, representing the remaining 4 third and fourth things surrounding the central atom. Once again, these lone pairs typically more repulsive than a bond. So from our perfect 109.5 tetrahedral angle, water is squished down to about 105 degrees or so. Subtle variations that let us know that our rules are consistent. Drawing water, once again, we have to worry about the 3-dimensional nature, but quite conveniently, you'll see that water is a planar molecule. All the bonds fit on the same plane of the page, so we only use solid bonds for this. There are some instances in which you may want to show this from like a head-on variation, but that's more work than I think you want to do. So you're welcome to show this as a planar molecule with just those 2 bonds as is. Let's make a molecule of carbon dioxide. Now this is a little trickier, mostly because now we have to worry about satisfying the octet rule for 3 different things. We'll draw a Lewis structure for CO2. Once again, we have carbon that has 4 valence electrons, and our 2 oxygens that each require 2 more shared valence electrons. Now, we could draw a Lewis structure to predict how to solve this structure, but again, our model gives us some physical intuition about how to solve this structure. Carbon, you'll notice, again, has 4 holes, requiring and demanding 4 bonds to it, and oxygen requires 2 bonds to it. So make me a molecule of CO2 without knowing the exact Lewis structure quite yet, and let's see what your little puzzling hands are able to piece together. So one thing I put for the idea that you cannot make impossible molecules out of these kits. If they fit together, it's a real thing that can exist. And the number of holes tells you how to satisfy this octet rule. Oxygen requires 2 bonds. Carbon requires 4 bonds. How to do that? How do we feel? Do we have CO2 molecules yet?
Is the red ball oxygen?
The red ball is oxygen, the black is carbon. So you need two red balls connected somehow to one black ball. The carbon needs 4 bonds, the oxygen each needs 2 bonds. I will tell you as a hint that this structure has no, carbon has no lone pairs. It only has 4 bonds. Just as methane has 4 bonds, CO2, the carbon, has 4 bonds. So my mother, who is an elementary school or retired elementary school teacher, said that the reason she became an elementary school teacher is because she wanted to be the person who had the solution textbook with all the answers to it. She also wanted summer breaks. Unfortunately, in my teaching position, I don't get summer breaks, but I do enjoy and I do delight in knowing the answers and seeing people arrive at the same sort of puzzling conclusion. So whatever you got, we're going to hold it up in 3, 2, 1. So we might have different structures. So your kit, again, there's physical intuition to how this model behaves, and they're designed to allow you to do things that are possible. And you notice that these slightly longer bonds are more flexible than these shorter, stubbier ones. And it allows you to not just anchor one bond between carbon and oxygen, but 2 bonds between this carbon and oxygen. So you'll see that by this arrangement, 2 bonds to each carbon, from carbon to each oxygen, it pulls itself into a linear shape, representing that there are 2 sets of things surrounding this central atom. From our Lewis structure, it helps us also, we can begin to get to the same answer, that our carbon, in order to satisfy the same challenge as before, has to be able to draw 2 bonds between this carbon and that oxygen, and this carbon and that oxygen. And while our Lewis structure is a little messy, we can clean it up ever so slightly to represent the idea that there is a double bond between each carbon and oxygen, and 2 lone pairs on each oxygen, pulls itself into a linear shape, really the only one that can be created by these molecular models. And again, we would predict that because these sets of electrons move together, there are a double bond going between the same atom, that the only way to satisfy that is for these to repel at 180 degrees. We'll also see that, depending on who you ask, is a realistic interpretation, that around this oxygen we see 1, 2, 3 sets of things, which causes the double bond and the 2 sets of lone pairs to arrange themselves more so in the trigonoplanar shape, 120 degrees more or less between the bond and the lone pair. Overall, a lot of our job really just is bookkeeping to account how many things, bonds plus lone pairs, recognizing again that any bonds between the same atom move together as a set, gives us a way to interpret what 3-dimensional shape this will adopt. And again, trying to draw those with these dashed and solid wedge bonds to represent this 3-dimensional structure here on a flat page. For this course, until you get to much more advanced topics in chemistry, we'll be mostly dealing with these molecules that have a maximum of 4 things surrounding it, 4 sets of pairs of electrons, or 8 valence electrons here. Again, sort of the best and well-behaved part of chemistry. Now, obviously, these molecules are quite simple, and you may have seen these before, but we can use this idea to also look at more complicated things, which invite us to discuss more advanced topics in chemistry. The last few things that we'll do is we're going to use our molecular model kits, and if you could be ever so kind to make me a molecule of ethanol, which has 2 carbons, 6 hydrogen, and 1 oxygen. If you are short on any of those things, sometimes these kits are not put back in correct order, let me know. But I believe you should have 6 hydrogens in stock. Now, as I said before, you can't make a wrong structure with this molecular model kit. But I will tell you that all structures are not necessarily the structure that I'm talking about. So give me your best idea for what a molecule of ethanol might look like. One little hint. Oh. If you're missing a short lone pair bond, let me know. But actually, that might be okay. So one little thing you might notice is that with more atoms, there's many more ways you might connect them. Again, you can't make a wrong structure, but the same molecular formula, C2H6O, there are many different ways that those nine atoms might be connected to each other. In particular, I want a molecule of methanol, which potentially helpfully might be written out in the structural formula, which sort of tries to give you the general shape of the molecule as CH3CH2OH. So make me a molecule of methanol, and then we'll compare our answers.
Yeah.
If you do end up, as part of your studies, taking organic chemistry as sort of the next course in the sequence, and don't shake your head until you get there. It's very handy. It's very helpful. As a chemical engineer, I greatly enjoyed organic chemistry. You will want to invest in one of these kits as these molecules become a lot more complicated. Additionally, if you want to deal with biochemistry, in which you have not just molecules of 9 atoms, but massive molecules, massive protein structures of thousands upon thousands of molecules, you will want a physical way to touch, feel, hold these atoms together. All right, does everybody have a molecule of ethanol? All right, well, I'll hold up our molecular ethanol in 3, 2, 1. Pretty good. Everyone sort of has a similar structure, but this is not the only solution to this structure. We sort of see again that this is a structural formula version of ethanol that spells out that we sort of have a chain of first carbon bonded to 3 hydrogens. Next in the chain is carbon bonded to 2 hydrogens and oxygen bonded to a hydrogen at the very, very far end. How we would draw this in 3 dimensions or 2.5 dimensions, again, take a moment to look at this structure and compare it to the structure we would show here. Which bonds are pointing away from us? Ones are pointing towards us. Which of these bonds lie flat in the page? Different ways to draw these, of course, different solutions to this Lewis structure. But we want to make sure that if we were to say ethanol, that we represent this arrangement of atoms, not a different variation, as different arrangements of atoms, even ones that have the same chemical formula, imply a different compound, a different substance. This molecule of ethanol has a boiling point of 78 degrees Celsius, slightly lower than that of water. We'll talk in the coming weeks about how we were able to predict that. But this arrangement of molecules is quite different than the same set of 9 atoms if you were to rearrange them into a molecule of dimethyl ether. Dimethyl ether still has the same chemical formula, C2H6O, but is an isomer, meaning same chemical formula, different 3-dimensional arrangement. So if you could be so kind, please rearrange your molecule of ethanol into one of dimethyl ether. You should use the exact same atoms, same bonds, but now rearranged into a different three-dimensional shape. There's more than one solution to this particular problem. Again, this structural formula, where ethanol was written out in one way, a hint of dimethyl ether structure is written out by CH3, parentheses 2, so two sets of those CH3, O, to give you some hints about how this molecule is arranged. It should be different than what your ethanol molecule looks like, as dimethyl ether is a very different molecule with different properties. These ethers very much related to sort of the ethers that old-timey surgeons would use to knock patients out. Has a very different structure, very different properties compared to ethanol, which old-timey surgeons would also use to knock people out, but for different reasons. All right, does everyone have some sort of dimethyl ether guess? So again, you can't make a wrong molecule, but you may not make this molecule we're talking about. So I'll hold it up, be proud of our work in 3, 2, 1. Wonderful. So, like ethanol, we still have the same sets of bonds, the same way to satisfy the octet rules. 2 to oxygen, 4 to carbon, 1 to each hydrogen, but there's different ways to arrange those three-dimensionally. Both these molecules do exist. And once again, take a moment to compare your structure of dimethyl ether with how you would see it represented on 3 dimensions. Make note of which bonds are flat and within one plane of the page versus which ones, particularly these CH bonds, are pointing out and into the page. Now, it is quite important that we get not just the chemical formula of a compound, not just the name of a compound, but we get all the way to being able to predict a structure, either by a more extensive molecular orbital theory treatment, or with sort of this pair of Lewis structures plus this valence shell electron pair repulsion theory. These molecular models do a lot of heavy lifting for us, so we don't have to get it all right off the bat. But we see that the different solutions to the same molecular formula, giving different isomers, that should be C2H6O, not H60, it's a completely different thing. These two different structures, same set of atoms, same satisfaction to the octet rule, give very, very different structures. As we move forward, 2 weeks from now, we'll concern ourselves with how would we be able to predict that even though they have the same set of atoms, same molar masses, same weight of these atoms, same weight of these molecules, that ethanol has a boiling point of 78 degrees Celsius. So at room temperature of about 25 degrees Celsius, ethanol is a liquid, versus dimethyl ether has a boiling point of minus 24 degrees Celsius. That at room temperature, about 25 degrees Celsius, dimethyl ether exists as a gas. Is quite more dangerous for the reason that it is quite volatile at room temperature. Ultimately, we need to be able to translate within our head, whether we're given the molecular formula, the name of the compound, all ultimately trying to get to the structure of this compound, because it's by this structure that we'll be able to predict something about its properties. In this case, the boiling point. Does it exist as a liquid or a gas or a solid at room temperature, being a quite important one. One final one. Let's make a molecule of acetic acid, which has the expanded structural formula CH3COOH. Give it a shot. Once again, you can't make a wrong molecule. And we must satisfy our octet rule, just as we have time and time again. But there may be easier and harder ways to do that. If you think you are without a sufficient number of connectors, let me know. but I think most people should be able to get there without looking at my solutions. So somehow, however you get there, carbon needs 4 bonds to satisfy its octet rule. Hydrogen, of course, needs 1. And each oxygen requires 2 bonds to go to it.
It's like a balloon dog.
A lot of molecules. It's like cloud watching. They all look like a thing. There are some very rudely shaped molecules as well that chemists love.
Okay.
For no other reason than it looks like a thing.
Like, what's an example?
There was a very serious paper published in a very prestigious academic journal reporting a synthesis that involved a ring molecule with one that was very long and had 2 clusters of atoms at the end. Yes.
Cool.
That's what people get paid good money to figure out. All right. How are we feeling? We've made a thing. We'll hold it up. Hopefully everyone holds the same thing in 3, 2, 1. Wonderful. Everyone has about the same thing. So you'll notice that our structure of acetic acid, which is the sort of chemical name of vinegar, once again satisfies the octet rule just as we had before, but requiring a little bit of guesswork to figure out that each oxygen is going to satisfy its octet rule in a slightly different way. This oxygen is going to have to do so by forming a double bond to the same carbon, but this oxygen may form 2 single bonds, one to a carbon, one to a hydrogen. In many cases, trying to go from just the molecular formula into a Lewis structure, takes much longer than I think any of you have time to do. A lot of your work and a lot of your job from here on out will be able to go from a chemical formula to either derive through puzzling through with molecular models or looking up a structure through your extensive Wikipedia research, but trying to be able to relate this 2.5-dimensional drawing, all the reasons why those bonds exist, of course, with a 3-dimensional representation, which will help us in our discussion in weeks to come. Now I want you to make a slight modification to your acetic acid, mostly in the recognition that if you were to look at the electronegativities of these various atoms, you'll find that carbon and hydrogen are very close in electronegativity, so we would predict it would have a polar covalent, or really a very closely non-polar covalent bond. Carbon-carbon being the same will have a non-polar covalent bond, and carbon and oxygen will have a polar covalent bond. So shared electrons between carbon, hydrogen, and oxygen. But if you were to compare those electronegativities quite carefully, you would see that the difference between oxygen and hydrogen is large enough that this is more so a ionic type bond, one that will more easily separate, in which our hydrogen will give up a electron completely to form H+, a hydrogen cation, and this oxygen will take that electron that was sharing previously to form an O- sort of end to this molecule. This, by losing this hydrogen, breaking the relatively weak OH bond, forms now the polyatomic anion acetate. So again, we see these polyatomic anions, or polyatomic ions, as a molecule now with a net charge. This now acts as one big anion that could potentially balance out a cation in an empirical chemical formula. Now there's something that happens quite interestingly. As we draw this structure, this molecule of acetate, you'll notice that as far as where these atoms are positioned and concerned, there really is no strong difference of where the atoms are located, whether or not this double bond is to the oxygen at the bottom, or if the double bond's to the oxygen at the top. As you rotate this bond, you'll notice that it essentially gives me the same structure, but sort of formally with a double and a single versus a single and a double bond. Now again, these molecular models give you real results. And it's no coincidence that these two are essentially identical structures. As far as the molecule treats it, after losing this hydrogen, each of these oxygens are identical to this molecule. What we'll talk about in the weeks to come, largely trying to go from the shape of a molecule to understand how it reacts and how it undergoes further transformations. One insight that we'll see is that sometimes we have several different structures, solutions to the same molecule, in which we may place bonds in different positions formally, single versus double, double versus single. Looking at this molecule of acetate, both of these, whether the double bond's pointing up or the double bond's pointing down, are valid solutions to this structure. And what happens and exists at the chemical level is not sort of a ping-ponging between these two structures. We again remember that the result of molecular orbital theory, that each of these bonds is actually this wave sort of structure. And every time a bond sort of is next to another bond, it can merge and overlap and mix with other ones. And we actually happen to have here, in which we have two solutions to the same structure, is that the real structure of acetate is an intermediate, a mixing of a double bond and a single bond between these two. What we actually have here is what's called a resonance structure. The idea that we don't have a single bond and a double bond, but those two bonds will tend to sort of mix together as orbitals do. And the actual sort of structure that you might see under a microscope is the same bond between carbon and oxygen, rather than a single and a double bond. Each of those sort of effectively has a 1.5 order bond. So slightly more than a single bond, slightly less than a double bond. You may think of this instead of one pair of electrons versus two pairs of electrons, 1.5 pairs of electrons, or 3 electrons between the carbon and the oxygen. The fact that this has further mixing of orbitals, which every time we mix orbitals, we have a stabilizing constructive interference, a destabilizing destructive interference, generally means that when we see resonance structures, we see more stable, lower energy molecules that are more favorable for various reasons. Now, the last little thing that we'll cover before we end with a good, healthy amount of time before our 2 p.m. deadline is that there's sort of a weird division at different levels of chemistry. Many chemists and people who go on to do research as scientists will use something like molecular orbital theory, which requires a little bit of thought, a little bit of time, and is definitely more predictive, gives you more accurate results. But many people are able to get away with a Lewis structure, but can only talk about really a very small subset of chemistry that follows this nicely behaved octet rules. There is a happy medium between those two, and we can recognize that these are orbitals that overlap and merge together without doing the full MO theory analysis. A compromise between the Lewis structure plus VSEPR theory, valence shell electron pair repulsion, that we have been using, and molecular orbital theory is what we would call hybrid atomic orbitals. This sort of takes the first result of MO theory that says that we can mix orbitals, not between different elements, but within the same atom. We could take our s orbital, mix it with the same atom's p orbital to rearrange them. Rather than have a spherical s and a dumbbell p, if we were to mix the s and merge it with the px, 2px in this case, we're now left with two sp mixed orbitals that are same energy, and of course two p orbitals that are unhybridized. What this allows us to do is that it gives us two orbitals, now equivalent in energy rather than an s and a p, that now point in opposite directions, and is of nice configuration that nicely overlaps with molecules that adopt a 180 degree bond angle. This allows us to recognize that these are bonds formed by overlapping orbitals, not worrying too much about trying to mix S with S and figure out how much it goes up and down, but now sort of adopting a way that allows us to map it onto our VSEPR theory, now through the guise of orbitals. So if we need a central atom bonded to two different things with a 180-degree bond angle, we might be able to form two equivalent sp orbitals that point in equal and opposite direction, reflecting mixing a s and a px orbital. If we need three things surrounding a central atom, we could do so by mixing one s orbital and two of our p orbitals, which gives us three sp2 orbitals that now point along those trigonoplanar directions, making it poised to bond to three equivalent things. This is another way we may think about this molecule of CO2, that this carbon, by having to bond to two separate things, two different oxygen atoms, is going to first mix its s and p orbitals to give these sp hybrid orbitals. Those conveniently point one towards each oxygen. The oxygen, having two lone pairs and forming one bond, is going to form a hybrid sp2 set of orbitals, giving us this particular shape, and sort of merging our look at thinking of orbitals from MO theory, molecular orbital theory, and Lewis structures, which sort of gets us to the answer faster, but has some gaps because of some of the assumptions that we might make. The final sort of way we might hybridize things, quite commonly seen for things like carbon, takes the four valence orbitals, one s, a single s orbital, and three p orbitals, and hybridizes those four orbitals together. Mathematically, the result that you get is a set of four sp3 hybrid orbitals that now point along those tetrahedral directions. What energy these sp3 orbitals are and how they are relative to hydrogen, for example, allows us to now look at the mixing of the sp3 orbital with the hydrogen's 1s orbital and do the same bonding, anti-bonding analysis. But we now sort of can deal with a more rational set of orbitals that gives us the result from valence bond theory of a tetrahedral shape to arrange these four different things around our central atom. So there are many ways in which we talk about predicting the rules for bonding. Ultimately, if you had the time and patience and a little bit of a computing time in the background, we would be able to predict everything with MO theory. It is the most authoritative. We have variations of that, either Lewis structures and valence bond theory, plus molecular models, to try to get to about 80% of the predictive power. We can have variations like hybrid atomic orbitals to try to further sort of patch up this theory, but it is quite difficult in many cases to be 100% predictive without very extensive computation, which is much more than I expect for this particular class. Problem set 3, which is being finished now, and will be posted later this evening, gives us sort of a very practical understanding of what I expect for you to take from this set of 3 different ways to predict structures. Again, a lot of it is to get to a point in which we can get to a 3-dimensional structure, so we can begin to talk about what the 3-dimensional shape means in terms of its properties. But there's a few ways that we can get there, and it serves you for your future to understand the different ways that different chemists and biologists and physicists and material scientists will get to this point with and without physical models. So, in the interim, between now and next week, we have no lab on Wednesday, so everyone gets a little bit of a breath between now and then. Take a moment to digest this. You're not expected to know everything about these bonding rules. Problem set 3, again, will give you a realistic understanding of what you're expected to take away from this week's lecture. Again, no lab on Wednesday. Go out there and celebrate Juneteenth. That lab report from last week, normally due the week after. You can turn in on Monday if you need more time with the calculations. I'll hang around here until 2 if you want help with problem set things before you turn them in, or calculations for your lab report as well. I am trying to edit our problem set 3 to represent the level of detail that we discussed today and sort of the content. So I'll try to quickly post that this evening. if not before. Do make sure you do it, as sort of this is sort of the one crack at a very important topic in chemistry that we get, and much of what we do builds off of this type of analysis. So do the problem set, read the textbook if you would like a second interpretation of what we talked about today, but we have some time to digest this complicated aspect of chemistry. With that, we'll call it a day. I'll hang around here until 2. Please sort of disassemble your kits, put it back in the Ziploc bag, and you can leave them up here for me. Thank you very much.